So in this video we're going to go over the symmetry identities for trigonometry. And what we need to remember is from our pre-calculus experience, we need to know what the definition of even symmetry is, or y-axis symmetry. So a function has even symmetry if it is a reflection of itself in the y-axis. And the way that we learned to test for even symmetry was to plug negative x, or the opposite of x, into f, the function f, and see if we got the same thing as if we just plugged in x. So for example, here you see that if you plug in negative 2.2 to the function or positive 2.2 into the function, you see that it generates the same output, 4.07. And we see that if we plug in negative 2 or 2, f of negative 2 equals f of 2 equals 0. Down here, f of negative 1 equals f of 1 equals negative 3. And this is kind of the hallmark of even symmetry. And visually, we can see that we have even symmetry if we look at a graph and we see that it is a reflection of itself in the y-axis. So the cosine function, it turns out, is a reflection of itself in the y-axis. We plug in negative pi or positive pi, the output's negative 1. We plug in 2 pi or negative 2 pi, the output's positive 1. So in general, we see that it doesn't matter whether we plug in x or the opposite of x, we get the same output. And the cosine function is a reflection of itself across the y-axis. And we can kind of understand why that's the case if we think about the unit circle, and we understand that really when we're plotting the cosine function, if we're being super careful, we know that this is actually the theta axis, and the outputs are the x-coordinates on the unit circle. That's what the cosine function is. So if you sweep through some angle theta and you get to a point x, y, you know that the cosine of theta is equal to that x-coordinate. And the key is if we rotate counterclockwise instead, which is just the reflection of this point through the x-axis, or theta axis, or x-axis, I'm in the xy plane here, sorry. So I rotate negative theta. Well, the x-coordinate is the same as it is here. The x-coordinate in quadrant 1 and 4 has the same sign. The y-coordinate changes. It becomes the opposite of what it was because the y-coordinate is now below the x-axis. But the key is when I rotate through an angle of negative theta, I still get the same x-coordinate that I got when I rotated through an angle of positive theta. So the cosine function has even symmetry. So this is true, which is why we're able to say that the cosine of negative theta equals the cosine of theta. Cosine function, reflection in the y-axis. Odd symmetry occurred when we plugged in the opposite of x, and we got the opposite of what we get when we plug in x. So cubing functions are usually the first place where we're exposed to odd symmetry. And odd symmetry is you can either think of it as rotational symmetry, so if you rotate by 180 degrees, points will match up, or it's a reflection through the origin, which is equivalent to a 180-degree rotation. And the key is, here if we look at the 1, we get f of 1, we get 2, but when we plug in the opposite of 1, we get negative 2, which tells us that f of negative 1 equals the opposite of f of 1. We get the opposite result. And this point here is a reflection of this point here through the origin. We can reflect these points through the origin and they'll match up. You plug in negative 2, you get an output of 2. You plug in positive 2. Sorry, we get an output of 2, and you plug in positive 2, we get an output of negative 2. So again, f of negative 2, that's a horrible negative 2. F of negative 2 equals f of the opposite of f of positive 2. We have odd symmetry. And this point reflected through the origin would wind up matched up with this point. So this was how we tested for odd symmetry. So the key is that the sine function and the tangent function both have odd symmetry. You pick a point here, like pi over 2. You see f of pi over 2 equals 1. And if we come over to negative pi over 2, we get this point here. F of negative pi over 2 equals negative 1. So f of negative pi over 2 equals the opposite of f of pi over 2. And this point here reflected through the origin is going to wind up right here. That's a horrible penmanship tonight, even worse than usual. The key is the sine function has odd symmetry, and we can justify the odd symmetry by thinking about rotating around the unit circle. So on the unit circle, as we rotate around, we rotate through some angle positive theta. We know that the sine function really is the y-coordinate. This is really the theta axis, and the input is really theta if we're being not sloppy like this picture kind of is. That's what I get for stealing a picture from someplace else. So the y-coordinate is the output. So you see here when you have f of theta, you get the output as y. But if we rotate the opposite direction, this point reflects down to here, and the x is positive, but now the y is negative. So we rotate through an angle of negative theta. We see that we get the opposite result. We get f of negative theta equals the opposite of f of theta. And the tangent function is going to wind up having odd symmetry as well, because the tangent of theta, we know it's going to be y over x. And clearly then if we plug in negative theta, we're going to get negative y over x. So certainly it's the case that the tangent of negative theta is the opposite of the tangent of theta. So it just comes from how the coordinates play out as we rotate through a positive or negative angle on the unit circle. So the key is that this definition of odd symmetry that we learned in pre-calc, we can now apply it to the tangent function. Hey, plug in the opposite of the angle, we get the opposite of the tangent of the angle. This is just the definition of odd symmetry. This is just the definition of odd symmetry, and that's why they're called the symmetry identities.